Remember we said that differential equations was a concept that we felt fairly certain would be a free response question on our test next May. So let's finish up work with differential equations with another approximation. Now, we've been dealing with graphical approximations because the basic idea behind slope fields is that we can find graphical approximations to solutions of differential equations even if we can't separate and integrate. We're going to use Euler's idea. He used the idea of the behavior of the tangent line, just like slope fields does, at a point, and the change that occurs from one point to another according to the behavior of the derivative. His is based on an algebraic manipulation of the derivative, which again is the slope of the tangent line. And he was able to find numerical approximations, not graphical approximations. His are numerical approximations to the solutions of those differential equations. So here's what Euler did just in general. Given an initial condition and a differential equation, dy dx equals whatever, the change in y over the change in x, rise over run. That's what we know the derivative to be, or the slope to be. So given an initial condition, Euler said that the change in y and the change in x had this relationship, all right? And he said it's based on increments and differentials, so dy and dx. If the slope at one point is known, a neighboring point can be approximated by extending the slope line to a new x coordinate using a small change in x. So he said if I have the derivative function and I have a point, I can find the slope through that point, dy dx. And then I can go over a small horizontal distance. Here we show a distance of 1/2. And I can use that information and the derivative information to find the corresponding change that happens in the y coordinate. So if I know the initial, and initial is x naught, y naught, if I know the initial y value, then all I've got to do is add to the change in y, and that will give me the new y coordinate. So x sub 1, that next output, is based on our initial x value plus a change in x. And he said our next y value, here we'll call it y sub 1, is based on taking the initial y value and adding that corresponding change in y. So we're usually given what the change in x is going to be. Euler called that the step size. The step size is our horizontal distance that we're going to go from our initial x value. So given a step size and given the differential equation, or the derivative, we can find the change in y and simply add that to the last, or the initial y value that we were given. So not all differential equations can be solved explicitly to produce an exact solution. Euler's method is used to approximate a solution to a differential equation if an initial condition is known. So here specifically, we're given dy dx equals x plus y. We're given the initial condition, x equals 0, y equals 1, and we're asked to estimate the function f of x where x equals 1. So we're in the plane at our initial condition, so we know that x naught, y naught is the point 0, 1. We know that the relationship between the change in y and the change in x, which are what these differentials are representing, we're interested in the change in y. I'm going to solve this for the change in y. So I'm going to multiply both sides by the change in x. So this is Euler's method. This is the power of Euler's method. He recognized that really all we're after is this vertical distance right here, because we know this slope, we can choose or will be given the horizontal changes that are going on, and we have an initial condition. So we can find the slope through that initial point, the slope dy dx, through the initial point x naught, y naught. And for us specifically here, that is if x is 0 and y is 1, that's 0 plus 1. So the slope of this line right here equals 1. And so the change in y is that slope through the initial point times the change in x. And they've told us our change in x is 1/2. So the change in y, this vertical change here, if we were to get the coordinates of this point, and look, that's a fairly accurate approximation. Here's the actual output of the function at at x equals 1/2, but Euler's approximation is pretty close. All right, so the change in y is 1/2. So here's what Euler said. If I start out with a y value of 1, and I know that that changes by 1/2, then this new y value, the coordinate, the y coordinate to this point, is 3/2. So here what we've found is we have found an approximation for the output of the function at x equal 1/2, because our initial x value plus the change in x gives us our new x value. So our initial x value was 0. Our step size, the one step we took horizontally, was 1/2. So the new x coordinate is 1/2. So the approximation to the function at x equal 1/2 is 3/2. All right, so remember, Euler called the change in the x value the step size. And we could recognize that the smaller the step size, the better our approximations are going to be. So let's take a look. Here it is all tied in together. And we found out that when x is 1/2, y is 3/2. So there's the coordinate of the point x1, y1. Now remember, we've actually been asked to approximate the function at x equal 1. So we need to take another step here. We need another change in x that is 0.5, and we need to find the slope through this point, right? And if we drop a horizontal here and have a right triangle, this will represent the change in y. And we know that our x coordinate now of this point, if we have 0 plus 1/2, this is where we were at x sub 1, then x sub 2 is going to be x sub 1 plus another change in x. So that's 1/2 plus 1/2. So right there in 2 steps, we get our x coordinate of 1. And that's what we want. We want the approximation of the output of the function when x equals 1. So we know right here, this distance right here is 3/2 or 1.5. And so if we could find this vertical change, that's going to be a good approximation to the function. So we know what x sub 2 is. We're after y sub 2. So this is how we found y sub 1. Remember, we said on the last slide that the next y output is the previous y output plus that vertical change. And we said the vertical change was the slope, the derivative, times a change in x. And that's based on this relationship right here. So if this is how we found the new y coordinate for x1, y1, how would we find the new coordinate for y2? Well, based on this, y2 is going to be the output at y1 plus a change in y. And a change in y is the slope through the previous point. So y sub 2 is actually y sub 1 plus the slope through x1, y1, because that's where we are in the plane right here at this point, and then times a change in x or a step size. So here's where we are here. So we know this point, y sub 2, which is actually the approximation of x equal 1, is the last y output, which we said was 1.5, plus the slope through the previous point. Remember, the slope was the sum of those of x and y. It was x plus y. So 1/2 plus 3/2 is 2. So there's the slope through the point x1, y1. And our step size is still 1/2. All right, so this is 1.5 plus 1. So there is Euler's method. There is Euler's method. There is a first example. Normally we don't draw pictures. I've just done this for teaching purposes. Euler's method is strictly an analytic method, and it becomes very important that you understand these relationships. Short of that, I'll just be really honest with you. If you will just memorize the formula for Euler's method, it will get you through the Euler's method problems. So here is a step-by-step process. You know I'm a process teacher. Here's the step-by-step process of how to get through Euler's method analytically. You're going to begin at the initial point x naught, y naught. It's going to be given to you. This will be given in the problem. You don't have to look it up. We know the initial condition. The next thing you're going to do is find the change in the y-coordinate from that initial point by using the differential or the derivative, dy dx, and the slope through that initial point. So we're going to find the slope and we're going to evaluate it at this x value and that y value. Then we're going to take that result and we're going to multiply it by one step size. That's what a change in x will be here. So once you have the change in y, all you need to do is add it to the previous y value, and that gives you your new y value. You'll repeat the process as many times as is necessary to approximate the value for the function, or for as many steps as you're asked to complete. So here is Euler's method. This is what you need to know. Make up flashcards, whatever you have to do. This is Euler's method. This is the first step in Euler's method. You'll be given x naught, y naught, and you are to find y sub 1. If you need to take additional steps, then we can see a pattern here. Let's say we had to take a third step. What would the third step look like? Well, it's the previous y value plus the slope through the previous point times a step size. All right? Now, this is a product added to this value. Lots of times students will take y sub 2 and add to it the derivative and multiply the whole thing by the step size. That's not what's going on here. All right? So let's work a couple of examples and then we'll do some homework problems. So here is our differential equation. Let dy dx equal 1 over x. Use Euler's method, and you do need to know this. This is what the AP is going to call it. Use Euler's method to approximate the y values with 3 steps, starting at point P naught, which is 1, 0, and letting dx, the differential, the change in x, the step size, be 0.1. So they tell us how many steps to take. They tell us what the change in x is. It's 0.1. They tell us what dy dx is, and they give us x naught, y naught. All right? So the first step is we're going to find y1. Remember, y1 is the initial y output, the slope through that initial point times a step size. All right? So we're going to have dy dx evaluated at x naught, y naught. So let's plug those in. y1 equals, you know what, I'm going to stop here. I see I'm about out of time. And so I'll stop here and we'll finish this on the next video.